So, we would kind of look into Morris and its this approximate counting paradigm and kind of try to show that with some more space you can get a nice epsilon delta algorithm. So, let us quickly brush up what we did yesterday. So, this was the basic algorithm. You had a stream and you have values epsilon delta. So, what you did was did an initialization step, x was the counter which was counting a certain element, and to implement this idea of counting the indices, we brought in probability here. So, I incremented x with probability of 2 to the power of minus x and outputted, I mean, as because of this 2 to the power of minus x. So, you raise 2 to the power of, because mind you my goal was to store the indices, right. So, 2 to the power of x minus 1, and that minus 1 is actually a correction factor needed for getting an unbiased estimator. Okay. Now, why do I need an unbiased estimator, or why am I proving concentration results around this? See, I want whatever answer my algorithm is giving, I want it to be exactly equal to the number of elements that it is supposed to count. But that I cannot do, because I have to, we've kind of proved an impossibility thing, that you have to at least give log n space to count exactly, right. I am not even willing to give log n space. So, what we are trying to is, we are trying to get to an estimate, so which will not be exactly what I am supposed to count, but I want it to be as close to that as possible, right. One measure is expectation. So, the expectation of my estimator, which counts using kind of log n space, if that estimator is an unbiased estimator, meaning thereby that its expectation is equals to what it was supposed to count, that we have proved as an unbiased estimator, right. Mind you, the output of my algorithm is a random variable. Why? Because it is dependent on that probability of 2 to the minus x. So, it is a random variable. So, that means the output estimate that you are throwing out is the outcome of a random process. So, it is a random variable. So, that means it is not going to take the same value again and again, right. It is going to take values over a range. Now, what I want to prove is that on the expectation, it will always be equal to the value that it is supposed to compute, that we proved yesterday. Now, it may be so that, well, think of this, that expectation is kind of an averaging argument, right. So, you can return the same average with very well spread out data, but you do not want that, right. You want your answer to be as close as possible to the quantity that you are wanting to estimate. That is the reason we need concentration bounds, right. So, we also proved certain concentration bounds in here and saw that, and for those, the moment I say that that your data is, I want to kind of get a measure or hold on how well spread the data is away from the expectation, obviously the thing that comes to your mind is variance, and we proved that the variance remains in this case for this random variable quite high, resulting in a bad outcome from your Chebyshev inequality, right. So, that is what we proved in the last lecture. Mind you, our goal was to get an epsilon delta algorithm like this. Yeah, that is where we ended. So, the error was something like 1 by 2 epsilon square, and we kind of convinced ourselves that this is no good, we are not doing good, right. So, that is greater than half, I mean probability only when epsilon greater than equal to 1, and epsilon greater than equal to 1 is too high a value, right. So, that is where we were in the last lecture. Now, as I said, we would take recourse to this fact from probability, that if I have a bunch of IID random variables and I take their average, the expectation remains the same. So, that means if I take independent runs of Morris, take their outcomes and take the average, it will still remain a unbiased estimator, right. This theory tells me that. But on the positive side, what I would get is that the variance would go down, that we have seen mathematically in the last class. But again, all good things in life come at a cost. What is the cost you are going to give? Space, because you are running multiple instances of Morris, fine. So, let us now formalize this thing. So, let me call it Morris plus. So, what I have? So, these are all my Morris. So, the same stream, so I have only one stream, right. So, it is being fed into parallel runs of Morris. So, these are say S many. So, this is like the first one, this is the second instance, this is, so let me call this space to be some S. The outcome of one is not dependent on the other. So, they are independent. So, this is the estimate that the first instance gives you, estimate that the second instance gives you, the estimate that the, so these are your S independent copies. So, what is the output of Morris's algorithm? So, it is a new random variable which is so our theory tells us that quickly figure out what is variance of NS. Oh, sorry. You should have told me, no? This is divided, this is an average. So, now there should be an S factor which was not earlier there, right. So, Anyone got the result? What should be this? Yes. So that is that we proved in the last lecture, it was n square, right? So I have it to be n square by 2s. So it's so we proved in the last lecture it was upper bounded by n square by 2. Now you have an s to be dividing it, right? That's what we saw, that if there are n IID random variables, the variance of their sum or the variance of their average came down by a factor of n. Okay. Now quickly see what Chebyshev is going to give us. Probability of ns minus n greater than epsilon n See, for most of the streaming algorithms, the algorithms would be pretty simple because your machine model is so weak that it cannot do much thing. So the algorithms would be pretty simple, but as again in life, if your algorithm is simple, your analysis would be pretty difficult to to get the desired result. Fine. So we have to get our hands dirty. Quick, what is this value? Let us see how much it is coming down by. Yeah, my calculation also shows it to be that 1 by 2s into epsilon square. Now see what I said, that I want a good error probability. For that I am spending space, right. So what I do is I set this error probability approximately to delta that I want. So now you solve this equation to know what is S. Got it? So the implication of this is, if you do this calculation, S would come out to be some theta of 1 by epsilon square delta. So if you have your space more than 1 by roughly 1 by epsilon square delta, then we are done. Now see what is happening, the input error probability term is dictating to you the number of instances of Morris that you would run, hence the space. Because you would store all these values and then compute the average. Done? Any doubts till now? Till now we have not used the Chernoff. We will show to you how we can use Chernoff here even to bring down the error probability even. So if you have doubts till now, get it cleared. None? Fine, let us move forward. So our takeaway from Morris Plus was, see, the moment you fix your delta, Morris Plus is fixed, because then you know what are the number of independent copies of Morris you would run, right. So the algorithm is kind of dependent on the value of delta. Fine. So just to have a sanity check, what is my space? Space is this, order of 1 by epsilon square delta, and you need a log n, right? That is your space. So that is Morris plus. Now we want to even improve further. So we do this Morris plus plus. What do we do now? Take the average of Morris pluses. That is not going to help, no? Because you are doing the same thing. You could have done that earlier as well. Now you need to get a little bit, what should I say, a little bit non-linear. The other thing was linear, right? So the trick here is, and this is an often repeated and used trick in streaming algorithms. So this is known as, the trick is actually known as the median of means. So what it, now think of this following thing. It's kind of a, think of this in a kind of a pyramidal structure, right? So the stream is coming. I had this Morrises, bunch of Morrises, ace one of them gives me a Morris plus. So what I will now do is run again multiple instances of Morris plus, say t many instances, take their median, and then argue via Chernoff. So what you now have is, so these are your Morris pluses. So that means each one of these bunches has S Morris sitting inside it, right? Say there be T independent copies. So each Morris plus would throw out for you a estimator, which was the sum of S independent copies of Morris. What I do is now, so what I do now is return the median of this T outputs from Morris pluses. Okay. So now the error probability is fixed to a delta. So say 1/3, fine. So that means each Morris plus is kind of taking, think of now delta as a constant. So each Morris plus is taking a space of kind of this 1 by epsilon square. Now why am I insisting on delta to be a constant? Because as I said, you fix your delta, you get a Morris plus, right? Because until and unless you fix your delta, you do not get your space, right? Because you need to run integrally many copies of Morris, right? So, you have to fix your delta, take suitable ceiling, floors, whatever, to get to know how many integral copies of Morris you would be running, right. So, now my delta is kind of, think of delta to be fixed. So, that has kind of given me concrete instances of this Morris plus algorithm. What I now do is I run T many copies of them. So, think of this in a pyramidal structure. Morris has so many S into T. I kind of bunch the first S, 1 Morris plus, next S, 1 Morris plus, so on and so forth. Then I get T many Morris pluses. Then I take the median of this output of T many Morris pluses and give you that output. So, say for example, think of our delta to be some probability value less than 1/3 or less than half. So, delta is a 1/3. Or maybe it's like, let me say that the error probability is 1/3, it's 2/3. So, what does this failure probability actually mean? That your this is failing with a probability of 1/3, right. So, the failure probability actually means this, that you are not getting close to your value with a probability of 1/3. Okay. So, once I have fixed this failure probability, this number of Morris plus instances is known. Okay. So, let me so how many of you have gone back and worked on deriving those Chernoff bounds? I deduced one for you and I gave you quite a few exercises. Devorshi and Uddala could kind of do those exercises, at least one of those exercises today. But how many of you, okay, forget about doing, how many of you tried? None. That's good. Okay, so let me kind of quickly give the particular Chernoff that we would be using. So, I mean, as I said when I was talking of Chernoff, it's like there are different variants of Chernoff bound. Which one you pick is kind of a judicious choice that you have to make as a designer, fine. So, the particular Chernoff I would use in here is the following. So, let me just give it to you because you have forgotten. So, 0 1 IID random variables, and the particular kind of Chernoff that I would use is this one. I think this was in the exercise, I suppose. Okay. So, again I give it to you as an exercise. Okay. So, mind you, so think binomial, t many instances. So, you fail for this. So, that means expectation of number of Morris plus instances that succeeds is greater than 2t by 3. Okay. Let me just use a 0 1 because I would finally apply a Chernoff. So, let me bring in a 1 0 random variable. And now, if you look at summation yi, what is this one? This is the number of Morris plus instances that succeeds. Done. Okay. So because of this, I can kind of mathematically rewrite this as expectation of y this is right. Done. Nothing serious going on till now. Okay. Now we would exploit the fact that we have taken the median, right. So what I have done is I have taken the median of this t instances, fine. Now the question is, can the median be a bad estimate? Because I have kind of taken the central most value, right. Now for the median to be a bad estimate, This is the crucial observation. Median is middlemost, right? So, if the median is bad, then whatever is less is also bad, right? So, for the median to be a bad estimate, at most half the Morris plus instances can only succeed, not more than that. So, you agree to this fact, right? Fine. Now, it is just a few lines of Chernoff. So, we have already defined what is the bad event in this observation. So, probability of so, I want to bound this. So, are you okay with this? If the median is supposed to be bad, right, not many can succeed, right, that was the argument. So, at most half can succeed, that is what I have written. Summation, and remember what was summation of yi is the number of Morris plus instances that succeeds. Okay. Now, this is not exactly in the form of Chernoff, right. So, I have to get it in the form of Chernoff by doing some calculations. So, I need this form x minus ex. Okay. So, for that what I do is I would maybe use this and use this, right, to do a quick calculation. So, if you subtract in here, this is what you get, right. So, you obviously have to have this in the opposite side, and then you can add the left hand sides of the two inequalities of the same type in the right hand side, and then you can get this one. Now, let me get back there and solve it. This is now nothing but I will use this. Now it's perfectly in the form of Chernoff. I take a mod, so it's something more. So the probability, this probability would be greater than the previous one, greater than equal to t by 6. Now this is perfectly in the Chernoff form that I wanted, right? X minus expectation of x mod greater than equal to some epsilon into mu. So apply this Chernoff with the particular values of epsilon and mu. You get this to be 2 to the power of e minus some t into some by some constant. So c is a constant. When you Chernoff gives you a inverse exponential, remember this, e to the power of something minus. So that c that I wrote there is a constant that is dependent on 3 mu etc etc. Set this to your delta. So okay. So what I have been able to do, I have been able to fix the space based on the epsilon and delta that's needed, right. S was dependent on 1 by epsilon square and t is now dependent on log of 1 by delta. Right. Now see, this epsilon and delta are input parameters. What I did was, the quantity that I got, I did set it to epsilon and I did set it to delta to figure out my space when I was jumping from Morris to Morris plus and then again from Morris plus to Morris plus plus. Fine. So you can now get kind of whatever error probability that you need, but you need to spend space for that. That is the takeaway. So this is the notion of an epsilon delta algorithm, and so this trick of median of means, what did it do? Mind you, your first error probability for Morris was this. So it had an error which was uncontrollable. You had no hold over it almost. In here, if you wanted to have a control over the error probability, you had to set 1 by 2 epsilon square equals to delta. But delta and epsilon are independent, which the user gives you. So your basic, so the point in here is, now if you think of epsilon and delta to be constants in 0, 1, so that means once an epsilon is fixed, the error probability of Morris is kind of a constant error probability, right. What Morris plus and hence Morris plus plus could do was convert this constant probability to some probability that you need. So it could get to an error probability that you need, but at the cost of some space, right. So what is your final space? So your final space is For the basic Morris you needed, think of this pyramid structure, for basic Morris you needed log n. To get to a Morris plus you need S equals to 1 by theta square, 1 by epsilon square, and for Morris plus this median thing you need another log of 1 by delta. So, this is what your space is. Professor Somasundaram, this goes up to 1245, is it? Yeah. Yeah. Okay. So, any queries before I move into a new thing? So, as you get into streaming algorithms would be pretty much simple, small, the pseudocode would be within 4-5 lines. The analysis would kind of be, have to get your hands dirty to do this kind of analysis, right. So, think of this probabilistic tools that we needed. We needed conditional expectation, we needed this knowledge of how does IID random variables help in getting unbiased estimators with less variance. We needed Chebyshev and Chernoff, right. So, again this router model, packets going. So, I would say with the caveat that if the previous thing has kind of mesmerized you, or it has been too heavy for you, forget about it, start a new thing which might again interest you, right. So, let us make a fresh beginning. So, the problem is distinct elements in the streaming model obviously. So, maybe your lecture on Monday and the tutorial would tell you that distinct elements is like has a lower bound of omega n. So, that means you need to store everything to figure out the exact number of distinct elements, right. Now, as I said, this is kind of an impossibility result, and impossibility results are mostly done through reductions. Now, what does this reductions tell you? Say for example, it tells you something like this, that I want to say prove say a bound for distinct elements. So, I am making a claim that if you in the streaming model, if you want to figure out the exact number of distinct elements, mind you the exact number, not approximate, the exact number of distinct elements, then there is no other way but to store everything. So, that means you have a lower bound of linear. The impossibility results are proved in the following way, that you get hold of a canonical problem somewhere. For streaming mostly, mind you, the lower bound, yesterday I was talking of a sorting lower bound, right. So, that was a lower bound on time. In here the lower bound is a space lower bound. This is not a, so it is kind of a different lower bound, but the idea of reductions remain the same. It says that, say for example, if you could solve this distinct elements problem in space better than n, asymptotically better than n, then you could have solved some other problem in some other domain which already has a standing impossibility result, because someone else has proved that impossibility result, hoping that the proof is correct, so that result holds. Say for example, distinct elements in your RAM model has a nice reduction to sorting. So, it tells you that if you can solve distinct elements in your RAM model in time asymptotically better than n log n, then sorting can also be solved in time better than n log n. So, that is going to violate that lower bound, hence your lower bound is what you assume. So, in streaming people prove this space lower bounds from problems in communication complexity. So, in communication complexity the setting is as follows: there are two players, say, and this world of communication complexity or cryptology, they always say it in terms of Alice and Bob, telling you, this is a science developed in West. So, you can think two Indian good names. So, the problem is as follows, that say for example, Alice has some 01 bits, right, and Bob wants to know something of there. Say for example, Alice has n01 bits and Bob wants to know what is the jth bit of Alice. You seem to understand this is a very innocuous problem. What the hell is there? But what I tell you is the communication channel is only in one direction from Alice to Bob, right? If it was a bidirectional channel, then J would have, Bob would have sent its J to Alice, and then Alice looks at what is the jth bit with her and returns it back to Bob. But the moment I say no, the communication channel is only in one direction, then see Bob has almost no way to know what is the jth bit of Alice until and unless Alice communicates its entire n bits to Bob, right. Now, this argument can be formalized using some information theoretic or counting argument to say that these things cannot be done in better than n space. So, this problem is known as index problem in communication complexity. So, there is another problem, say equality. So, Alice has an n bit string and Bob has an n bit string. You want to know if these two strings are equal. Again, no other better thing than communicating everything. Now, again there is a catch. So, see the method which Alice and Bob uses to solve this problem is known in communication complexity as a protocol. So, Alice and Bob devises a protocol to solve this problem. Now, the question is, in the protocol, are Alice and Bob allowed to use randomness? If they are not allowed, then I say that the protocol is a deterministic protocol. If they are allowed to use randomness, then it is a randomized protocol. Now, as you see, there is magic in randomness. So, the moment you are allowed randomized protocol, then you can do better than, mostly you can do better than, in some of the cases at least, you can do better than deterministic protocols, right. So, I talked of an problem in index, I talked of equality, then there is a problem called disjointness. So, Alice has a say bit vector of 0 1, Bob has a bit vector of 0 1, and you want to figure out whether, so think of this. So, this 0 1 vector can be thought in terms of a set inclusion problem, right. Say for example, you have a set on n elements. So, think of this, you have a set of and your bits are 0, 1, 1, 0. So, that means you are talking in terms of a subset. 0 means do not include that element in your subset, 1 means include that. So, your new subset is 2, 3. So, you can think of any 0 1 bit over n bits as a new subset. So, the question is, Alice has a string like this, Bob has a string like this. For the sets that they represent, whether there is a common element or not, right, meaning thereby that there should be two ones in corresponding positions that match. So, this is known as the disjoint problem. So, these are kind of canonical problems in communication complexity, and people can prove lower bounds there. So, in streaming what you do is you use those, make reductions from there to your own streaming problem, which Uddalak and Devarshi would do for you on Monday, to show lower bounds in streaming, right. Okay. So, this is kind of a very overall idea of impossibility results. Now, so I start by asserting, not proving, that distinct elements has a lower bound of omega n. So, that means I do not have much hope other than to store everything. So, what I will do is fall back to that epsilon thing. So, let me try to get an estimate. Fine. So, throw up ideas. Yeah, come up with ideas. Yeah, come up, throw up some ideas. So, I have a stream sigma of m elements . So, see, the number of distinct elements would have been m if all of the elements in the string would have been unique, right. So, that means for some elements there are many repetitions in this string. So, let S be the set of the elements that form the distinct elements of sigma, right. So, S is obviously a subset of n universe. So, what is our goal? Done. So, say your elements are 1, 2, 1, 2, 3, 3, 1, so on and so forth. Then S is the set only 1, 2, 3. So, S is the set of distinct elements that I get from sigma. So, my goal is to estimate the cardinality of S. That is what finding distinct elements is all about. Okay. What do you do? But how can you compare? Then you have to store. So we set ourselves a target of space, say log n. Binary array. How big that array has to be? For which elements should you store? For which elements should you store? See, the point is to estimate S, the number of distinct elements. It might be so that a single element is repeated multiple number of times and the other elements are repeated a very small number of times. So, any kind of this averaging argument would not work, right? Because you have to count the occurrences of numbers which occurred very less number of times as well as elements which occurred multiple times. That also adds up to 1 in your S. The numbers which occur very, say maybe even once, also adds up 1 to your cardinality of S. That is the problem. So, any kind of averaging argument which kind of looks at this summing things is not going to work. See, approximate counting was a nice thing. So, an addition would work. In here that is a problem. Fine, as we are encountering some problem, let us make one assumption. Assumption is S is sorry. So, this is nothing but 1 to n, right, this set. So, I give you this assumption that S is not anything arbitrary, but it is a subset of this n numbers selected uniformly at random. Now, can you do anything? So, somewhere is your n, here is your 1, this is your this numbers over the real line, this S was selected so that means what I am making, the assumption that I am making is this set of distinct numbers that you get from n is kind of uniformly spread in the interval 1 to n, right. Batch the stream, how do I batch? As I said, averaging arguments are not going to work here. You understand the highly, this problem has a highly, what should I say, a non-linear structure to it, or rather does not have a linear structure to it. So, if you are going to batch the elements which are, an element which has occurred many number of times, say close to linear number of times, you have to detect it, right. So, then you have to store almost all occurrences, all distinct occurrences, right. So, now, but if I make this assumption of S being uniformly picked uniformly at random from N, so that means, again all these are probabilistic speaking, these are kind of very high level ideas which I will kind of finally mathematically formulate. Then these elements of S would be very uniformly spread in this range 1 to N, right. So, let me mark them, yeah. Hashing for what?
We want to find the distinct elements.
Yes.
So whatever we find, the way we are selecting an element, let's say one is there.
So, you are not working under this assumption S is uniform at random. So, what are you hashing exactly? Yeah, there must be some reason. We are studying this just after Venkatesh talked of hashing. It will use hashing, but what do you hash? Hash is kind of a function. So, you have an input. Hash is a function that you have to nicely design. We will see. Hold on. So, let us first look into this assumption that S is kind of uniformly spread in this region, right. Okay. Now, what I do is kind of mark this. So, this is kind of the first element from S, this is kind of the second element from S, this is kind of the ith element from S, I plus 1th element from S, and this is the last element from S. So, I just mark them on this line 1 to N. So, these are also this indices of S, they are also integers, fine. Okay. Now, as because they have been picked uniformly at random, these intervals should be of almost same length, right. Fine. So, think of these members of S as kind of guards or sentinels which you have placed on the line 1 to N. So, how many such intervals should be there? Hey, how many such intervals? If you place 1, how many intervals do you get? 2. So, if you place S, you get S plus 1, right. The number of intervals. What you said was how many elements are there in each group. So, each partition has how many elements? Right? Elementary arithmetic, not even mathematics. Done? Okay. Is this going to help me in any way? Is this idea, I mean, whatever I have done till now, is this going to help me in any way? Focus on this part. So, if you look into this S1, what I have marked as S1, now if I want to look into the rank of S of 1 in 1 to n, that rank is this number, because we have argued that in each partition there are roughly this n by s plus 1 many numbers. So, that means if I look into the first partition, so if I look into this first partition, the rank of S1 is n by s plus 1, right. So, that means the n by mod s plus 1th number is nothing but S1. Agreed? Again, these are all approximate arguments which I will kind of formalize later on. Agreed? But also fine. What does S1 being the minimum number in S means? S1 is also the minimum number in the stream, because the stream is only formed out of numbers in S. So, this implies so that means can we do this? As the stream comes, it is very easy to do, right. Always check with the, so this is like similarly as the RAM model. So, let that minimum be marked as some L. So, now you know L is equals to, sorry, n by s plus 1. L is what you have got out of your stream and the rest are parameters, right. Mod s is the number that you want to estimate. So, solve for modus. So, this is how much? N minus L, N by L minus 1, right. Was this idea not cute? So, do you have any difficulty in understanding this idea? If you have, I will go through it once, but then probably I will use her idea to give you the punchline, which will actually solve the problem. See, every deduction that I did rested on the assumption that S is uniformly at random spread in N. Then so any doubts, let me know. So, the problem is solved, but for the fact that this assumption is not a very good assumption. If this assumption is done, it is fine, but assuming that the distinct elements are uniformly spread in the universe, so that means you are restricting your input, that your input can only be of particular type. But I want to solve this problem for any general stream. So, that means I want, this assumption gives this idea that I want a domain from which I will pick the universe, from which I will pick my distinct elements such that they are kind of uniformly spread. So, now what I will do is I will take recourse to this hash function. So, the domain of the hash function is the set of natural numbers, the universe from which your stream comes. I will pass it through a hash function of certain degree of independence, what we will see later, right. So, that means now your domain has changed. It is no longer N, it is a new domain. So, this range of the hash function. So, we will talk in, so to kind of simulate this assumption, we will need a hash function that goes from this to something which we will see later. Now, what will happen? As the stream comes, any element that is repeated will hash to the same location, fine. Two elements that are not same will with high probability not go and collide. But if this hash function is suitably chosen, then these hashed values would kind of be uniformly at random in the new universe created out of this hash function, right. What is this hash function doing? Taking the elements in N and kind of distributing them in a new universe, right. But because this hash function is nicely chosen, it will distribute for this stream, only these distinct elements are coming. So, these distinct elements would now be very well spread in that domain. So, now my algorithm is pretty simple. As the stream comes, I just store this hash function. What kind of hash function we will see in the afternoon. Store a hash function, Venkatesh has possibly talked that storing a hash function means storing certain coefficients of a polynomial. So, you just store those coefficients of a polynomial suitably chosen from an universe randomly chosen from a universe. So, this is your hash function given. Each element of the stream comes, pass it to the hash function and let it go. So, as hash, values in the sigma comes, you hash it and just figure out the minimum. As because this hashing kind of simulates this assumption, then the rest theory goes through. I will later on prove to you that my estimate of distinct elements is not very far from the exact number of distinct elements. So, that we will do in the afternoon. Any questions? It's kind of magical, no?
You want to store it in order of logging state, which is a constraint.
What am I storing? Only the hash function. So, this hash function would be such that it can be stored only in log n bits. So, I will show that I just require a polynomial of modulo something where I just need 2 coefficients. Yes, so that means 2 wise independence should hold. Right.